Is the roll sheet still moving around? March 4th. Anybody know what day March 4th is on? Which one of these is a Friday? March 4th. March 4th. So it must be 4/2. All right, so let's get started here. I modified our learning guide a little bit last night, and I looked at some things and I thought, oh, March 7th, we'll be done. We can probably have the test March 4th. And then after I went through more last night, maybe I did that wrong. So this was the original date. So it's either going to be here or here, and this will be chapters 1 through 3. Okay, the original date was the 7th. I thought, because I don't want to start the new material too much to get into that before the test. So we'll just see how this goes. Okay. All right, let's review here, and then we'll see. We'll see if we got questions on the quiz. This right here. So if we name this, this is an acid that has oxygen. Now, you can go, I was going through OWL last night. You can go into chapter 3, part 2 of OWL, and it does naming acids. And both of those OWL assignments are open. So if you want to look ahead, you can go in and do this already. So this right here, and I think OWL does a molecular name first. And the molecular name for this would be hydrogen nitrite. So it does a molecular name column and it does an acid name column. And then the name out of this would be, like to us, so this would be nitrous acid. Again, you can skip ahead and OWL and do that. Hydrofluoric acid, if it starts with hydro, ends in ic, it is not going to have oxides in it. So this is going to be H+1, and this would be the same as IBE, right? So this is going to be HF. The molecular name for OWL is going to be hydrogen fluoride. Okay, boy, I didn't leave much room for number 3. Fine. Now, this is a question that I don't want you to, you shouldn't spend much time on this. if you have the test. So here's what I'm saying. Please, please, please redo quiz questions. Redo some things. So you need the molecular formula. You're given the molar mass, and here's the empirical formula. So you just need to find this multiplier here, which is going to be 236.2 grams per mole divided by the empirical formula mass. So carbon, 12.01, 1.01, 16.00 will work. 36.03 and 3.03, 36, 39.05, and this would be 55.09. What is the answer to this? 59.05. So this looks to be 4, right? So if that is 4, I can't believe I didn't leave any room for this. So if that is 4, you would end up with C8, H12O8. Okay, and also chapter 3, part 2 and all, it does a lot with figuring out the oxidation number at the end. And we'll have a conversation about oxidation reduction, but we're going to review that in this problem as well. So which of the following is written correctly? So for this, we can assume that this here is a chloride. So that makes this 10-3. Is there a 10-3? No, there's not a 10-3. We have NO2 in parentheses, and that NO2 is -1, and you've got 3 of them. That gives us -3. +3 would have to be the magnesium, and magnesium is only +2. So that's junk. Let's go down to this one. This would be chloride again. That would be a -4. This would have to be an iron 4. And there's no such thing as an iron 4. This is sulfate. -2 times 3 gives us a -6. So this would be a +6. This would be manganese 6 sulfate. And that should work. Okay. So again, in all, you end up with like KMN. This is a very common one. So if we wanted to figure out the oxidation state of Mn in this, this right here is -2 always. That gives us -8. Potassium is always +1. So this manganese is a +7. It could have also, Al does this, I believe, as well. It could give you MnO4 minus and say, find that. Which is the exact same thing. It just doesn't have a positive ion with it. So in this case, you want it to equal -1 because that's the ion charge. So this gives you -8. So this would still be a +7 here. Okay, that would still be a +7. So sometimes it wants the oxidation state when it's a compound or if it's an ion. Okay, let's look. We've got this baby due Tuesday. So is there any final questions on this? And the chapter 3 one, I'll try to get out tonight. I don't have it tonight. So this is, you're just going to input your answers in this, right? All you're going to do is put your answers in. They should be, unless I messed up, There's a couple of people done this. It's the exact same question. And this diagram here, I don't know why I've loaded this a couple of times. I think it shows up online. I don't know why it didn't show up here. Any final questions on this quiz? Yes. 15. Ooh, 15. Yes, that's a good question. 15. What mass of barium contains the same number of atoms? So the key, if it's the same number of atoms, it has to be the same moles. Same number of atoms would be the same moles. So we can take this right here. This is my lithium. So how many grams of lithium in 1 mole of lithium? Now that will give 2 moles of lithium. But if you have the same number of atoms, we can convert this to atoms, but it's going to be a wasted step. Sorry. Then you can just make this barium. And then you can go 1 mole of barium to grams. We could actually calculate out the atoms again, but we would convert that right back to moles anyway. So the same number of atoms really means the same moles. That should do it for that one. Anything else on this, baby? Okay, we are going to look now then at chapter 3. And as we start chapter 3, this is how OWL starts out with diagrams like this. So for chapter 3, part 1 of OWL, it actually has the pictures on the screen like this. Shut that down. My bad. So we know that on the left side here, we have reactants. And on the right side here, we have our products. And this arrow pretty much just means yields. Produces, yields, whatever you want to call it. And when you enter things in OWL, this, you can just click on a gas. These are all gases, but they're all right there. One thing I should change my ways is I always write the ions as like barium +2 instead of 2+. In OWL, I believe on some 2+ all the time. Okay, so here's what we've got. We know that this right here is a carbon based upon what this looks like. And then we have hydrogen, 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 and a hydrogen. So if the whites are hydrogen, then we know we've got hydrogen here, hydrogen here, hydrogen here, and hydrogen here. And this is my carbon again. And oxygen, of course. I don't know if this red's going to show up. Oxygen, 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 oxygen. So the question is this reaction balanced? So as you do this, and we're going to work on some on the next page, we have 1 carbon on this side to start out, and we have 1 carbon on this side to start out. we have 4 hydrogens here on the reactant side, and we have 2 plus 2 here. We got 4 hydrogens total on this side. Oxygen, we have 1, 2, 3, 4. And we have 1, 2, 3, 4. So we would say that this reaction is balanced. Now, in OWL, you're putting these 2's in here and everything to balance it. These are coefficients so that we have the same number of each atom on both sides. And when you're all done, you should be able to put an equal sign in here. And if we did carbon, we had 1 carbon, 1 carbon. And then you can do an equal sign with oxygen. You've got 4 and you've got 4. So it's pretty easy in all. They'll have gas, liquid, AQ for aqueous and so on. And this is exactly what it looks like. They do phosphorus, chlorine, they do different compounds, so it looks like this. So that's the first 2 sections of and again, we are doing this to make sure we are consistent with the law of conservation of matter. So products on the right of the arrow, reactants on the left. In order to make sure it's balanced, we put coefficients in front. Now, we do not put numbers in between here. The coefficients go perfectly in front. And to get the total atoms, you always multiply. Like this right here means you have 2 oxygen, right? 2 O2s, or 2 times 2 is, you get 4, right? We're always multiplying. Okay. 3-2 is balancing equations. And I wish OWL would give you something like this. So this is the order that you should balance equations. So it should be compounds with polyatomic ions. Now, what do we mean by that? Do you have sulfates? You have nitrates, and so on. You have ammonium. Compounds that have polyatomic ions you should do first, because then you're taking care of 2 atoms at the same time. You'd be balancing sulfur and oxide. Metals, where are the metals? Left of the staircase. Do we have a good staircase line in the periodic table I handed you out?
On one side.
One side. Here's our staircase line. Why is that only on one side? So to the left of this bold staircase line, we have our metals over here. We know we have non-metals over here, but we are not going to have compounds with the noble gases. So your non-metals are going to be in this area right here. Okay. Then you want to do non-metals except hydrogen and oxygen, then hydrogen, then oxygen. Just leave oxygen till the end, because all these polyatomic ions, not all of them, most of them have oxide in there. It is going to be the highest, most complicated number. So if you leave oxygen to the end, a lot of times you're done by the time you get there. Okay. Example, write a balanced equation for the reaction of molecular nitrogen and oxygen to form dinitrogen pentoxide. So we'll write this out first. Molecular nitrogen, N2 gas plus O2 gas yields N2O5. I'm hoping that's a guess. I don't know for sure, to tell you the truth. Now, we do not have any polyatomic ions in here, right? There's no nitrates, phosphates, nothing in parentheses. We don't have any metals. And if we want to do oxygen last, we better do nitrogen first, huh? But we have 2 nitrogen and 2 nitrogens, so that's good. Now oxygen. 2 here, 5 here. In order to make them the same, the least common multiple is going to be 10, right? So we are going to have to put a 2 here to get 10. Again, we're not putting any numbers in the middle of compounds. You cannot do that. And a 5 here. And now that changed our oxide or our nitrogens. So now we have 2 times 2 is 4 nitrogens. So we need 2 there. Now, what this really means is we have 2 nitrogens. So you have N2 plus N2 plus O2 plus O2 plus O2 plus O2 plus O2. Now you realize we don't write them out like this. And you get N2O5 plus N2O5. Isn't that what that really means? This is why we can multiply all the time. 5 times 2, there's 10 oxygen, right? 10 oxygen here, or 2 plus 2 plus 2 plus 2 plus 2 gives us 10. All right, let's go to this. This one here is a combustion reaction. And I should make a comment on this though. You will see there is 7 diatomic molecules. Mostly gases. And di meaning 2, so they are hydrogen gas, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. So you will see these written by themselves with a 2 as diatomic molecules. Okay, let's do the next one for this combustion reaction. So we have C2H6 plus O2, H2O plus CO2, carbon dioxide plus water. And this is just very typical of a combustion reaction where you have CXHY plus O2. You can have different numbers of carbons and hydrogens. So if we balance this, where should we start? Carbon. We got to stay away from hydrogen and oxygen. Do them last. So 2 carbons, 1 carbon. Put a 2 here. Now we'll do hydrogen. 6 hydrogen here. 2 hydrogens here. 3. How many oxygen total on the right side? Total. 7, right? We've got 3 times 1 is 3, plus 2 times 2 is 4. 3 plus 4 is 7. However, whatever number I put right here, I'm going to end up with an even number of oxygen on the left side. No matter what number. If I put a 2, it's a 4. If I put a 3, it's a 6. I put a 4, it's an 8. It's going to produce an even number of oxygen. So we have to produce an even number of oxygen over here. So in order to do that, we're going to double everything and come back here. So we're going to change this to a 6, 4. This has to be a 2. And the magic number now that goes in front of the O2 is 7. Because now we have 14 oxygen. Okay, so a combustion reaction looks like that. Carbon plus hydrogen, or carbon, hydrogen, oxygen. You get water plus carbon dioxide. And that's the last part of OWL. Let's look at this reaction. This is lead acetate, and we could also write the acetate as CH3COO. If we balance this, this is beautiful. Why is it beautiful? Because we have polyatomic ion of acetate. So if we treat that as 1 unit, we're balancing 3, or we're messing with 3 different elements at the same time. So with this 4 right here for acetate, this is only 1 acetate here, correct? This is 4. So I am going to put this right to here. I'm going to put a 4 right there. That is going to do my acetate. So polyatomic ions first. We just did that. Next, we should do metals. What metal do you want to do? Lead. Lead. 1 lead, 1 lead. What metal should we do next? Sodium, right? 4 sodiums here, 2 sodiums here. 2. Now we should do nonmetals. Sulfur. 2 sulfur here. 2 sulfurs there. It looks to be this thing is done. Hydrogen and oxygen, there's 12 for the hydrogen, 8 for the oxygen. This thing is balanced. Okay, let's do this one right here and see what we got. We have polyatomic ions all over the place here in this one. We got hydroxide. We've got ammonium. And we've got phosphate. Polyatomic ions all over the place. So it doesn't matter which one we pick necessarily. It'd be nice to pick one with a large number first. Like here's 3 ammoniums, 2 phosphates. I would try to deal with the 3 ammoniums first. Okay, so if we do the ammoniums first, 3 there, and only 1 ammonium here, we put a 3 in front. But now that affects my hydroxide, my OH. So let's tackle the OH. I have 3 OH here and 2 here. So that's not going to work. Let's make them both 6 now. So I need to make this a 6, and I need to make this a 3. Now let's go back, because now that changed my ammonium. I have 6NH4, 3 here. Let's make it 6 here, so 2. Now all my polyatomic ions are balanced. I've got 2 phosphates. I've got 6 ammoniums. I've got 6 hydroxides. That's done. I've got 3 baryons. I'm good. We're good there. Some of these combustion ones can get ugly. You can end up with a 25 here and things like that. Yeah, we'll do this one. We'll start with carbon. 5. Twelve hydrogens, 2 hydrogens, 6. And oxygen's next. How many oxygen on the right? 16. 5 times 2. 10 plus 6. 16 oxygen on this side. So what can I do with this? I've got this odd number right here, don't I? So let's see. I cannot put a 8 here. That's going to give me 17. Let's try to make this number over here even. So let's try this. Actually, I probably shouldn't have did that so soon. We can always reduce it, which we might have to do here. So over here now, I'm going to have 32. So now I've got 32. What number can go here to get 32? We got to put a 15 here. Because 15 times 2, 30. Plus the 2 right there. So you end up with 32 on both sides. Now again, that's still a combustion reaction. It's got oxygen in it. That's kind of ugly. All right, let's go to the next page. We are just going to talk about this in case you see it. I wish we delved into this more, but this, so far, we've only talked about reactions, and we just assumed that everything went product to reactants, and the reaction is done. But we know reaction rates are very, very different. Iron doesn't rust just like that, right? But you have done reactions before where boom, it's done. Well, this is a reversible reaction. So I put this diagram on here just to go through this a little bit. So first of all, SO2 plus O2, this has a double arrow. This is called the forward reaction. So if an SO2 combines with an O2, we get SO3, right? However, if an SO3 splits apart or decomposes, we can get SO2 and oxygen back, right? Now, let me give you an example real quick of a reversible reaction that you know about. Let me try to simplify it for you. Here's my beaker, or my glass, doesn't matter. Here's my glass. And inside that glass, I have a H2O liquid down here. And what's going to happen, you know that if you keep the top off of this, all of that H2O is going to evaporate, right? So the reaction I could write is H2O liquid, don't write any of this down, would go to H2O gas. That would be a valid reaction. It would take a while for all that to evaporate, correct? And we could affect the evaporation rate with temperature. And that is exactly what happens at the microscopic scale, by the way. You have a molecule of H2O moving this way and another one moving up, and it hits one from underneath and gives it just enough energy to what I say jump out of the liquid. What if you do this? Seal that sucker up. Within a short amount of time, you're going to get more and more H2O gas built up here. But at the same time, you're going to have some that are going to be moving towards this, get bumped from the sides, whatever. And some of them are going to go from H2O gas back into the liquid. Makes sense, doesn't it? They're going to crash into the liquid surface and be trapped. So you would agree that this reversible reaction would also take place. And hopefully you would agree that within a certain amount of time, if about 1 billion per second go this way, about 1 billion per second would go this way, and the amount of H2O gas up there would stay constant, even though this would go on forever. The reaction would never stop. Agreed? It would never stop if it was sealed up. Even though, again, 1 billion per second going this way, the forward reaction, at the same time, 1 billion per second going the opposite way. So that's an example of a reversible reaction. So here's an example here where this is on the product side. So this is my product. This is a reactant. And this is a reactant. So it looks like this reaction starts. Now there's two ways to start it. You could start with just SO3 and let the reverse reaction take place, or you can start with both reactants. And in this case, this starts with both reactants, right? This is my product. My product right here starts out at 0 at time 0. So you put in the two reactants, and kind of like what my evaporation example was, after a certain amount of time, it reaches equilibrium. And once it reaches equilibrium, concentrations do not change, even though the reaction is still going. The net effect is the concentrations do not change. So that's an example of a reversible reaction. Okay. Now, coming up in lab is going to be all about electrolytes. This week is gases. Make sure you are looking at the videos before you're going to lab. There's videos out there that goes through the lab. So make sure for lab you're looking at those videos. Well, what about when substances are dissolved in water? They undergo either a physical or chemical change that yields ions in solution. These substances constitute an important class of compound called electrolytes. Substances that do not yield ions when dissolved are called non-electrolytes. If the physical or chemical process that generates the ions is essentially 100% efficient, all of the dissolved compound yields ions. Then the substance is known as a strong electrolyte. If only a relatively small fraction of the dissolved substance undergoes an ion-producing process, it is called a weak electrolyte. So for a weak electrolyte, you are going to get few ions. Figure on the next page shows the dissolvent of KCl in water. It says the polar water molecules are attracted by the charges of the potassium and chloride ions. The electrostatic attraction between an ion and a molecule with a dipole is called an ion-dipole attraction. We'll look at that on the next page. If water can overpower the electrostatic bond forces between the positive potassium ion and the negative chloride ion, the ions split, and we say that KCl is soluble. This process represents a physical change known as dissociation. So we know that the easiest one that you know is table salt. Solid. You know that you can see solid salt crystals with the naked eye. You add salt to water, the salt disappears. It is still in there. What does it do? It splits up into individual ions. We write AQ for that, plus Cl minus AQ. You cannot see individual ions moving around in there, but it's all in there. And you know it's all in there because you can evaporate the water and get your solid back, right? So we are talking about this whole concept of whether or not something dissolves. And if it does dissolve, does it produce ions? So here is potassium chloride. It would be the same as sodium chloride. Now, we're going to learn towards the end of the semester this concept about bond dipoles. So in this case, though, I can put it to you this way. I draw water as Mickey Mouse. And we know it takes a pair of electrons to make a bond. So you're going to hear me talk about this coming up. So this is what we're going to do for Lewis structure for water towards the end of the semester. We know it takes a hydrogen electron and an oxygen electron to make this bond. But it turns out that they do not share those electrons equally. Oxygen pulls the electrons, those bonding electrons, towards itself. And if oxygen pulls those electrons towards itself, then the oxygen is going to be negatively charged. And the hydrogens are going to be positively charged. When we say this molecule is polar, it has an unequal sharing of the charge. And that is the case with water. That's what makes life on this planet possible. That is why your snowflakes are 6 sides. That is why when water freezes, the density changes and it creates a larger volume. So notice the water is going to come in and the negative chlorides are going to get attracted to the positive hydrogens here. And the positive potassiums are going to get attracted to the negative oxides. And as that's moving around in there, if water has the ability then to pull these apart, then we say that this compound, potassium chloride, is soluble or it dissolves. If water does not have the ability to pull these attractive forces apart, it's insoluble and does not dissolve. If you produce a whole lot of ions, like NaCl, you are going to get electricity to flow through this solution to beat heck. You're going to get a very strong light bulb. Few ions, probably the best example is vinegar. And vinegar is CH3COOH. You're going to see this coming up a lot. Or HC2H3O2. And no ions. I don't know, let's see, some compound like this. Or something that does not dissolve in water at all. Summarize, strong electrolyte. If it is a strong electrolyte, you're going to get a whole bunch of ions. Strong acids would work. HCl would work. You are going to get a lot of ions. If you have a weak electrolyte, you barely get a few ions to split off, and otherwise no ions. Let's go to the next page. How do you know something dissolves? How do you know something dissolves? This is the ion compound dissolved in water. This is what you're going to see with OWL. So you don't have this in the learning guide. I added it last night, so I just put it up here. So all sodium, potassium, ammonium salts are soluble. Water is going to split them apart. All nitrates, acetates, chlorates, perchlorate salts are soluble. All chlorides, bromides, iodide salts are soluble, except those containing lead, silver, mercury are not soluble. This is the chart you want to be referencing. If you are not sure, I have on the back side of the pink sheet a solubility grid. And the solubility grid looks like this. So we just said that according to those solubility rules, potassiums, sodiums are soluble. This, I call it the cheater's grid. I also have one or two of these at the end of the learning guide. But this is what your textbook uses, and this is what OWL uses. So this is what I'll reference back to quite a bit. So if you go into the learning guide or OWL and you just want to snip this, I just snipped this right out of OWL. Actually, I didn't snip it, I cut and pasted it right out of OWL. And maybe I'll send you a summary, I don't know. So next time we meet, we are going to talk about net ionic reactions, which what OWL does. And we will go from there. I will try to get out this chapter 3 quiz to you tonight. Okay. And I might not have it done, but I'm going to get out what I do have done.